Our first speaker will be Khalid, also known as Raigon. They are really into the nitty gritty when it comes to programming, from how game engines are built, including Fabled Engine, to building a small custom entity component system. Currently working as a sole indie developer on a secret CRPG game from the ground up. Outside their professional endeavors, Khaled enjoys reading general fantasy and does some research and development. Without further ado, I'll let them take it away.
Okay. So, hey everyone. Today I'll be talking a bit about optimization. My name is Khalid. If you guys still don't know who I am, I guess I'm Raigon on the Discord server. So this is not, I guess, a talk about low-level optimization or instruction-level optimization, even though it has a little bit of that inside the slideshow. It's just a simple way to optimize your game so you can kind of get like maybe 3x or maybe 4x times for your game. So, all right. So a little bit about me, I guess. Daniel already said a lot. I worked on a little toy game engine in Rust. I'm not sure if I'll be continuing that. I created a sparse set ECS system, which is pretty cool. And I guess the current projects I'm working on right now is the 3D CRPG game, and I wouldn't call it a sparse set ECS system. I would just call it an entity component system. All right, so I guess these are just general principles that I follow when I program. I guess the first one is specific problems require a specific set of solution, and a specific set of solution requires a specific set of data. And data may be generic in type, but it is never generic in purpose. So whenever you have use different data, that's not for your, I guess you're trying to solve the problem with, then you're not solving the problem. I guess we'll continue from there. The more context you have, that's for, I guess, the code and the data, the more better your solution will be. So generic data diminishes context. And avoid premature complexity. I guess that can be from feature creep or something else like that, because you don't have a solution for the future, right? Keep it right now to the present. I guess let's write the simplest code for the specific problem. Remember, simplicity is better than being clever, even when you're optimizing. And I guess the next one is you will uh is it this guy right here? No, no. Yeah, this is a PDF, so yeah, it's okay. And then you will read your code more than you'll write it. So write for readability, not for like low-level optimization. Okay, so the first one we'll be talking about is memory. There's, I guess, a little battle between which one's faster, stack and heap. But I guess for me, they're both relatively the same. They are both on flat virtual address. The stack isn't a magical form of memory that differs from the heap. Um, this whole notion of the stack is somewhere up, and the heap is a little below. That's really not the way to look at it. That's kind of like segmenting the virtual address, and segmentation was back in 32-bit and 16-bit times. We don't use segment registers anymore. It should be one big storage of virtual address space. It's flat. The only difference is the implementation. I will continue on what I mean by that. So if you look at the stack, I guess there's three factors to look in the stack. The size of the allocation, it's fixed, which is around 1 megabyte usually. There's no resizing, so you don't have to move memory around. The lifetime of the memory is known. It's tied to the function scope. So, and the usage of the memory, it kind of reuses the memory for each function scope. So that is very good because we'll look at later how there's also some sort of cache for memory, which is called translation look-aside buffer. So I guess another thing is when you're using the stack, it accesses it sequentially. And usually when people use the heap, it's not very sequential, so it jumps around. So that can cause, I guess, TLB misses or whatnot. And just looking at it right here, you kind of see it. This is hexadecimal, so it's going up 8 bytes. It's loading, and then from here it's storing. I guess don't kind of look at this like something very complicated. It's just a representation of what the stack's kind of doing. So I guess when we're using the memory, we can simply follow these. Everyone knows this. This simple, I guess, notion where we minimize the amount of waste created. We only store the necessary piece of data we need inside memory because memory is still kind of slow even though we have TLB. We reuse it because we have a TLB, which is like a cache. And if we keep on reusing the piece of memory, then it's always going to be a TLB hit. And then we recycle it. We keep on, I guess, when we are finished with the data, then inside the memory, we can just keep on recycling it, right? So I guess this is a PS, keep allocation size to page size granularity, because the computer loads and stores data in bulk. The TLB is 4096 bytes. So when you're allocating a piece of memory, that's 4096 bytes. So might as well just allocate the whole thing. And then these are just syscalls for the allocating pages. All right, so data layout. Data layout is very important. When you're creating structs or classes, there's usually padding depending on how the data is laid out. That's to optimize, I guess, fetches, so it doesn't go to the next cache line, or if it doesn't have to read 2 cache lines or any. It just tries to optimize it by making it aligned. So this is kind of a simple fix. Is if we organize the data where the highest size is first, followed by the lower size, then we can kind of avoid padding. There's usually going to be padding at the end, versus if we keep the data all over the place, then the padding is kind of everywhere. And that's kind of problematic because the padding, even when if it's getting loaded into the cache, then it's also going to store the padding, which is wasted space. All right, so data flow is important as well. I guess specific solution is derived from the data layout and data flow. A good way to think of it is the direction of the data. You have input, you transform it, then you have output. And then for the transformation, how the data is changed, a good way to think about it is how is the data changed through the transformation, and is there any dependencies where one transform or one piece of data depends on each other. An example here is like data flow is a conveyor belt system where an item goes in, what order, and if the ordering matters or not, and the data layout is like the boxes. And PS instructions are just data as well. All right, so the next is cache. When the CPU loads data in the L1, L2, or L3 cache, it does so in a fixed size called cache line, typically 64 bytes. Even if your program requires 1 bit or 1 byte, it still loads the full 64 bytes of cache line. So the best thing to do is to, I guess, make use of all 64 bytes. For example, if you're loading a struct, but you just need one, let's say, int 32, it's going to load 64 bytes of other piece of data. So it's good to keep all the used data together, I guess, keep it not scattered around, but keep it all together. And then the way it's used as well, if it's used, you want to organize it in a way where it's sequential. So it's using one, then it's using the next and next and next. And then for memory, memory is loaded as page size granularity. That's 4096 bytes. It's stored in the TLB, which is like a cache for memory. And each entry in the TLB stores 4096 bytes. The TLB works like a cache for virtual to physical address. It prevents page walks, and one major advantage of this design is memory. You can reuse memory. So if something's in the TLB and you reuse it, well, it's going to go faster than for you to allocate another piece of memory and then use it, because it's probably going to have a page fault or something, and then it has to be cached in the TLB. The TLB is organized in multiple levels, typical L1 TLB and L2 TLB. That's very good, because now if you allocate a lot of memory, then it might cause eviction on the L1 TLB, and then later on when you try to access it, it's going to go slightly slower because it's in the L2 TLB. And worst case is if you need the piece of memory but it's paged out to disk, you're going to be paying a significant cost. So the TLB is here to help you. So yeah, use it, I guess. So I guess we have a general idea now kind of cache and TLB. So go big and be predictable. Use a lot, not just single bits or bytes or U32s, and be predictable in it. Be sequential, or be it in a specific pattern. Try to avoid padding. That's going to be wasted space. Try allocate in those, I guess, granularities that the CPU works with. Use all the data, which is a win, because if it's an L1 cache, that's a huge, like, nanoseconds. Access sequential or in a predictable pattern. You have a prefetcher, so it's very smart. It'll kind of pick it up, and it will prevent, I guess, cache misses because it will prefetch ahead. Avoid dead data, and load once and use often. I guess takeaway, solving, that sounds very complicated, all the, I guess, information I gave you, but this kind of really helps me. It's not like in a sense where it's like optimization, it's more like a guideline that I follow. First, I give a brief informal statement of the problem. Then I specify the correctness condition required of the solution. So what's the input data that's fed in the transform? What's the output data that I get from the transform? What's the constraints, which are like mandatory rules the transformation must follow? What's the limits, such as the memory limit, time limit, array size, or other pieces of limits? What's the assumption? Because assumptions are very crucial. For example, our strings UTF-8 are the UTF-16. And what's the goal of the transform? Well, what's the goal of each transform? And then from there, I implement the solution. And then I check the solution if it actually is solving the problem. And then from there, I just profile and do some optimization on it. And I guess that's it. And then I got a few principles just right here if anybody wants to look at it.